There is a border around everything you have ever seen. Not a wall made of stone, not a glowing edge floating at the end of space, not a place where a spacecraft could arrive, turn on its lights, and look over the side. It is quieter than that, stranger than that. It is a limit drawn by time itself. Every star, in every photograph, every galaxy, in every deep field, every faint red smudge that took almost the entire history of the universe to reach our telescopes. All of it belongs to only one region. It is the part of the cosmos old enough, bright enough, and close enough for its light to reach us. Beyond that region may be more galaxies, more darkness, more empty space, more versions of cosmic history we will never record. Maybe the universe continues almost exactly as it does here. Maybe it changes in ways we have no language for. Maybe the question itself breaks down, because the word beyond may not mean what it seems to mean when space is expanding and the observer is trapped inside a horizon. That is what makes this mystery so unsettling. The universe does not simply hide things behind distance. It hides them behind the rules of seeing. Before we begin, if you enjoy calm space documentaries like this, subscribe to the channel, leave a like, and write in the comments where you are watching from and what time it is for you right now. Somewhere on Earth it may be morning, somewhere it may be late at night, and all of us are looking out from one small moving world into a universe that refuses to show itself completely. Tonight, you are watching the Just About Space channel, talking about what lies beyond the universe we can see. To understand what may lie beyond the visible universe, the first thing we have to remove is the image of an edge. Human minds like edges. A room has walls. A country has borders. An island has a shoreline. Even the sky seems to have a ceiling when clouds hang low over the ground. So when we hear the phrase observable universe, it is easy to imagine a huge sphere of galaxies with a final outer surface, as if everything known is packed inside a cosmic bubble, and outside that bubble, there is a different place waiting. But the edge of the observable universe is not an object. It is not a shell. It is not made of matter. It is not the outside of creation. It is a horizon. A horizon is not the place where Earth ends. When you stand beside the ocean and watch the water meet the sky, the line in the distance looks real, but it belongs to your position. Walk forward, sail forward, fly forward, and that line moves with you. Another person far away has a different horizon. The ocean continues, but each observer sees only a limited part of it. The cosmic horizon works in a similar way, but instead of being caused by the curve of Earth, it is caused by the finite speed of light and the age of the universe. Light is fast, but not infinite. It crosses the distance from the Moon to Earth in a little over a second. It crosses the distance from the Sun to Earth in about 8 minutes. It takes years to travel between nearby stars, thousands of years to cross a part of the Milky Way, millions of years to arrive from nearby galaxies, and billions of years to reach us from the deepest fields our telescopes can study. So when we look outward, we also look backward. The galaxy you see 10 million light years away is not shown as it is tonight. It is shown as it was 10 million years ago, when its light began the trip. A galaxy 1 billion light years away is seen 1 billion years in the past. The deepest galaxies are not just distant locations. They are ancient records, frozen into the beam of light that finally reaches our instruments after traveling across most of cosmic history. This means the visible universe is not a map of everything that exists right now. It is a collection of messages that have had enough time to arrive. That alone changes the question. If someone asks, what is on the other side of the universe, they may picture a boundary in space. But the real boundary is a boundary in information. We can only know about places whose signals have crossed the expanding distance between there and here, since the universe became transparent enough for light to move freely. And that is already a strange phrase, transparent enough, because there was a time when the universe existed, but ordinary light could not travel through it the way it does now. In the early universe, matter was so hot and dense that electrons and atomic nuclei were not yet joined into neutral atoms. Photons kept scattering from charged particles, like light inside a glowing fog. Space was filled with radiation, but it was not yet a clear window. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons and nuclei to combine. Light was released. That ancient glow, stretched by cosmic expansion into microwaves, still fills the sky today. We call it the cosmic microwave background. It is often described as the oldest light we can see. That sentence sounds simple, but it carries a hard limit. When we look far enough in every direction, we do not see stars, because stars had not formed yet. We do not see galaxies, because galaxies had not assembled yet. We see a surface of ancient radiation, the afterglow of a universe that had just become transparent. Behind that surface, if behind is the right word, the universe was not empty. It was just opaque to the kind of light we use for astronomy. So the first wall around the visible universe is not the end of space. It is the beginning of visibility. Imagine trying to see across a city on a foggy night. The buildings beyond the fog may still exist, but your eyes receive only a glowing blur. The limit is not created by the absence of streets. It is created by the condition of the air between you and them. In cosmology, the fog was the early universe itself. This is why the observable universe is not the whole universe. It is not even the whole universe that may have existed at the moment the oldest light was released. It is only the part of that ancient surface whose light has reached Earth by now. And Earth is not special in this. A planet in a distant galaxy would have its own observable universe. Its cosmic sphere would overlap with ours, but not perfectly. Its observers would see some regions we cannot see, while losing some regions visible to us. Every location carries its own light horizon, like every ship at sea carries its own visual horizon. That is one of the most important ideas in this entire question. There is no central viewing platform. We are not sitting in the middle of a physical ball called the universe. We are sitting in the middle of what we can observe, because observation radiates around the observer. The visible universe is centered on us in the same way your personal horizon is centered on you. It looks centered because you are the one looking. The universe beyond what we can see may not be a different realm at all. It may simply be more universe whose light has not reached us and may never reach us. But before we go there, we need to understand why distance in cosmology is so much stranger than distance in ordinary life. If the universe is around 13.8 billion years old, it might seem obvious that the farthest visible things should be no more than 13.8 billion light-years away. Light travels 1 light-year in a year. The math appears finished before the mystery begins. But that would only be true if space were sitting still. It is not. Space has expanded while the light was traveling. A photon may have left a young galaxy more than 13 billion years ago. But while it crossed the universe, the distance between that galaxy and us grew. The light did not travel through a fixed stage. It traveled through a stage that was stretching under its path. By the time the photon arrives, the place that emitted it can now be much farther away than the light travel time suggests. That is why the observable universe is often described as about 93 or 94 billion light-years across, even though its age is less than 14 billion years. This does not mean light moved faster than light. It means the scale of space changed. The difference matters. If you imagine galaxies as sparks flying through a static emptiness, cosmic expansion becomes confusing. But in modern cosmology, galaxies on very large scales are carried apart by the expansion of space itself. They may have local motions of their own, but the largest pattern is not ordinary travel through space. It is the growth of distances inside space. The deeper we look, the more this expansion reshapes what we see. Distant galaxies appear redder because their light has been stretched. A wave that began as ultraviolet or visible light may arrive as infrared. A galaxy that once shone with young stars can appear as a dim red object at the edge of detection, not because it is intrinsically weak, but because the universe has pulled its light into longer wavelengths and spread its energy across time. That is why powerful infrared telescopes matter. They do not merely make distant things brighter. They search in the wavelengths where ancient light has been shifted by the expansion of the universe. Each improvement in telescope design pushes us closer to the earliest galaxies. Each deeper field adds detail to the record of cosmic dawn. But no telescope can remove the basic limit that light must arrive before we can use it. A perfect telescope could not photograph a galaxy whose light has not reached us. A perfect detector could not measure a signal outside our causal past. This is where the mystery becomes less like exploration and more like captivity. We are locked inside a region of information. We can improve our instruments within that region, but we cannot demand messages from beyond it. The universe is not refusing to answer because we are too primitive. In some cases, it may be unable to answer because the answer has no path to reach us. That is the first terrifying truth about what lies beyond what we can see. The unknown may not be unknown temporarily. It may be unknowable in principle. The next step is to imagine the observable universe as a sphere around Earth. But we have to be careful. The word sphere is useful, yet it can mislead. It does not mean galaxies are arranged inside a glass ball with Earth at the center. It means that in every direction, there is a maximum distance from which light has had time to arrive. Look north through the sky, and there is a horizon. Look south, another horizon. Look toward the galactic center, through dust, stars, and distant galaxies. And beyond all of that is the same ancient glow. Look in the opposite direction, away from the Milky Way's crowded center, and the oldest light also waits there. The cosmic microwave background surrounds us because we are looking back to an early time from every direction. It is not a shell located around us in ordinary space like a wall. It is a shell in time. It shows the universe at a particular young age, seen from here. If you could instantly travel billions of light years away, your view of that shell would change. You would still be surrounded by a cosmic microwave background, but it would not be exactly the same sphere we see. Your ancient light would come from a different set of regions. This makes the phrase, "the universe we can see," deeply personal. Our observable universe is ours, not in a mystical sense, not because Earth is important, but because observation depends on where and when you are. The full universe, if it is larger than the observable region, does not orbit around our view. Our view is a small cut through it. That idea can feel humbling, but it is also useful. It helps prevent the wrong question. We should not ask what is physically outside our bubble as if our bubble were a container floating in emptiness. Instead, we ask what may exist in regions separated from us by horizons, distance, expansion, and time. There are several possible answers, and some are calmer than others. The simplest answer is that beyond the observable universe, there is more of the same. More galaxies, more clusters, more superclusters, more cosmic web, more voids, more dark matter, more faint galaxies forming, merging, and fading according to the same physical laws we see here. This is not a boring answer. It is actually one of the most enormous ideas in science. The part we can observe is already so large that human imagination fails almost immediately. It contains hundreds of billions of galaxies, each with billions or trillions of stars, depending on the galaxy. It contains Vast, dark spaces between clusters, long filaments of matter, invisible halos of dark matter, ancient light, exploding stars, black holes, planets, dust, and the chemical history that eventually made worlds like Earth possible. Now imagine all of that as only the visible patch. Beyond it, the same cosmic structure may continue for distances we cannot measure. There may be galaxies whose light began traveling toward us, but because expansion keeps stretching the distance, that light will never arrive. There may be observers out there looking at their own skies, unable to see us for the same reason. Two islands of visibility can exist inside the same larger universe and remain forever separated by the growth of space. This is not science fiction. It follows from the same logic that makes the observable universe finite, while the whole universe may be far larger. The calmest answer may be, beyond our horizon, the universe continues. The frightening part is, even if it continues normally, it may still be forever lost to us. Because there is a difference between existence and accessibility. A galaxy can exist and still be unreachable. A star can burn and still never send us light from its present day. A civilization could rise somewhere beyond the cosmic horizon, build telescopes, study its own ancient radiation, ask the same question, and remain permanently absent from our sky. It would not be hidden by choice. It would be hidden by geometry. At this scale, loneliness does not require emptiness. The universe can be filled with things and still keep them apart. That is one of the reasons the boundary of the visible universe feels so different from any ordinary frontier. A frontier on Earth invites travel. A cosmic horizon may forbid it. We have crossed oceans. We have crossed deserts. We have left Earth's atmosphere. We have sent machines beyond the planets. Each of those journeys was difficult, but the destination remained inside the same shared present. The problem was engineering, danger, and time. The cosmic horizon is different. No engine can make a signal arrive before it exists in our past. No spacecraft can travel into a region from which even light moving towards us can never reach us. The issue is not only that the distance is large, the issue is that the expansion of space changes what distance means. This is where the title of the video becomes more than a poetic question. What lies beyond the universe we can see may be real, physical, and ordinary in its own neighborhood. But for us, it can behave almost like another universe, because no information from there can enter our instruments. If science is built on evidence, then beyond the horizon is where evidence thins into inference. We do not stop thinking there. We do not stop building models, but we must accept the boundary between measurement and speculation. That boundary is not weakness, it is honesty. The best cosmology does not pretend to have eyes outside the observable universe. It uses the patterns inside our visible region to ask what larger space is likely to be like. And those patterns are strange. On the largest scales we can measure, the universe appears remarkably uniform. Not perfectly smooth, but statistically similar in different directions. Galaxies cluster. Voids open. Matter forms a cosmic web. But when averaged over huge enough regions, there is no obvious edge, center, or preferred direction. This idea is often called the cosmological principle. On large scales, the universe is homogeneous and isotropic, meaning broadly similar everywhere and in every direction. It is not a law carved into reality. It is a working assumption supported by observation across the visible universe. It says that we should not assume our patch is special unless evidence demands it. If that assumption holds beyond our horizon, then the unobservable universe is likely more of the same. Our visible region would be one sample from a much larger cosmic fabric. But a sample is not the whole object. If you see one small patch of ocean, you can infer that water continues beyond your view, but you cannot know every storm, island, depth, or current hidden past the horizon. The same is true here, except the ocean is space-time and the horizon may never be crossed. There could be regions beyond what we see where matter is arranged differently, but still obeys the same laws. There could be extremely rare structures so large that none appear inside our observable volume. There could be enormous voids, dense walls of galaxies, or ancient patterns that our patch is too small to reveal. And if inflation happened in the early universe, the amount of space beyond our visible region could be vastly larger than the part we observe. That brings us to one of the most important clues in the entire story: cosmic inflation. Inflation is the idea that in the earliest fraction of a second, the universe expanded at an incredible rate. It was not an explosion into empty space. It was a rapid stretching of space itself. This idea helps explain why the observable universe looks so uniform in regions that, without inflation, seem like they should not have had time to exchange information. It also helps explain why space appears so flat on large scales. If you take the surface of a sphere and zoom in close enough, it can look flat, even though the whole shape is curved. In a similar way, inflation could have stretched the universe so much that any original curvature became almost impossible to detect across our visible region. But this creates a powerful possibility. If inflation stretched space far beyond what we can see, then the observable universe might be a tiny patch inside a much larger inflated realm. How tiny? We do not know. It could be only somewhat larger than what we observe. It could be enormously larger. It could be so much larger that the entire visible universe is like a single grain of dust compared with a continent. That is not a number we can simply measure with a telescope, because the evidence has to come from inside the horizon. Inflation turns the question beyond the visible universe into something deeper. It does not merely say, there may be more galaxies out there. It suggests that the full cosmic region may be vastly beyond direct observation, and the part we see may be only a local consequence of a much larger early event. This also changes how we think about the Big Bang. The Big Bang was not a point in space from which matter flew outward. It was a hot, dense, early state of the universe everywhere in the observable region. If the universe extends beyond what we can see, then those regions were also part of their own hot, dense, early state, at least if the same history continues. There is no outside direction from the Big Bang, in the ordinary sense. Every distant galaxy is not moving away from the place where the Big Bang happened. Every location was once part of that hot, early universe. Expansion is not debris flying from a central blast. It is the growth of distances everywhere. This matters because many people ask what is outside the universe, as if the universe were an explosion expanding into a pre-existing room. Modern cosmology does not require such a room. Space itself is the thing expanding. So the question what lies beyond the universe we can see should not be confused with what lies outside space. Those are not the same question. Beyond the visible universe may simply mean regions of space beyond our observational horizon. Outside the universe would mean something else entirely and may not even be a meaningful phrase in physics, unless a specific model defines it. This is where language begins to strain. Words like outside, edge, center, beyond, before and after come from everyday life. They work well for houses, mountains, roads, and clocks. But the universe is not an object sitting inside a larger room we can step around. If all physical space is part of the universe, then asking what is outside all space may be like asking what is north of the North Pole. The grammar continues, but the map ends. Still, the observable universe gives us a real boundary to discuss. We do not need to solve every metaphysical problem to say that our view is limited. And that view has layers. The first layer is nearby space, the moon, planets, asteroids, and comets. We can reach some of these with spacecraft. The second layer is the stars around us, measured in light years. The third is the Milky Way, a disk of hundreds of billions of stars. The fourth is the local group, with Andromeda, Triangulum, and many dwarf galaxies. Beyond that come clusters, superclusters, walls, filaments, and voids. Then, as we look deeper, galaxies become younger, their shapes change, their light shifts redder, heavy elements become less common, the universe becomes more primitive. Near the farthest visible galaxies, we are no longer looking at mature cosmic structures like those around us today. We are studying the early chapters of galaxy formation. Then, beyond the first galaxies, we reach the cosmic dark ages, before stars filled the universe with light. Then, we reach the cosmic microwave background, the afterglow of the hot young universe. That is not merely a distance marker. It is a time barrier. If we had different kinds of detectors, we might look beyond the CMB in other messengers. Gravitational waves from the very early universe, if detectable, could carry information from times when light could not move freely. Neutrinos might also preserve ancient clues, although the cosmic neutrino background is extraordinarily difficult to observe directly. This means the visible universe is not only limited by light in one simple way. It is limited by the messengers available to us. Electromagnetic astronomy has one horizon. Gravitational wave astronomy may have others. Particle astronomy may, in principle, reach different epochs. But none of these give us a magic view of regions whose information cannot reach us at all. Different messengers can reveal earlier times. They do not automatically reveal unreachable places. This distinction matters for the future. Humanity may build telescopes in deep space, interferometers larger than planets, detectors hidden on the far side of the moon, gravitational wave observatories separated by millions of kilometers, and instruments that can measure faint signals we have not yet imagined. Those tools may transform what we know about the observable universe. They may reveal the first stars in more detail. They may map dark matter more precisely. They may measure the shape of space with better accuracy. They may test inflation. They may find patterns in the ancient radiation that hint at processes before the hot Big Bang phase. But there will still be a horizon. Better eyes do not remove the speed of light. Better maps do not stop cosmic expansion. Better equations do not turn inaccessible regions into observed data. This is the quiet frustration at the heart of cosmology. The subject is enormous, but the evidence comes through a window of finite size. And yet, that finite window is unbelievably rich. Inside it, we can measure the background glow of the early universe. We can count galaxy distributions. We can watch supernovae reveal cosmic acceleration. We can measure how matter clumps under gravity. We can compare the abundance of hydrogen and helium to predictions from the early universe. We can use the cosmic web as a fossil of primordial fluctuations. From inside the window, we reconstruct the room. But the room may be part of a mansion, or an endless city, or a structure whose global shape does not resemble anything we can picture. That brings us to the second possible answer to what lies beyond what we can see. Maybe the universe is finite, but unbounded. This idea sounds impossible at first because finite usually means edge. If something has limited size, we expect a boundary. A table has edges, a field has fences, a planet has a surface. But geometry is not always that simple. The surface of Earth is finite in area, yet if you travel straight across it, you do not reach an edge where the ground stops. You eventually return to where you began, because the surface curves around itself. That is a two-dimensional analogy. Our universe has three spatial dimensions, and if space has a certain global curvature or topology, it could in principle be finite without having an edge. In such a universe, traveling far enough in one direction might eventually bring you back to your starting region, though not necessarily in any practical or observable way. Light might circle around space, producing repeated images of the same galaxies from different directions, if the universe were small enough and shaped in the right way. Astronomers have looked for signs like this. So far, the observable universe appears very large compared with any possible wraparound scale we could easily detect, and the evidence is consistent, with space being flat or nearly flat on observable scales. But flat on observable scales does not prove infinite. It only tells us that if there is curvature or wraparound, it is not obvious inside our visible patch. A giant room can look flat from one corner. A vast sphere can look flat if you see only a tiny part of its surface. This means beyond the visible universe could include more space that eventually loops in some way, or more space that extends forever, or more space whose shape is simply too large for us to measure. The hard part is that global shape requires global information, and we do not have access to the whole globe. This is one of the most unsettling truths in the question. The universe may have a shape, but that shape may be larger than the evidence available to any observer inside it. A fish in a small pond can learn the local water temperature, currents, depth, and chemistry. It might infer something about the pond. But if the pond is connected to a sea beyond a narrow passage the fish can never reach, its local measurements may never reveal the full geography. We are not fish, and cosmology is far more powerful than that analogy suggests. But the limitation is real. We can ask if the universe is infinite. We can test curvature. We can search for repeated patterns. But we may never receive a final photograph of the whole. And if we cannot see the whole, then beyond the visible universe becomes not a single place, but a set of possibilities. One possibility is ordinary continuation. Another is enormous but finite space. Another is infinite space. Another is a universe with regions so distant that their physical conditions differ because inflation or other early universe processes varied from place to place. That last possibility moves us toward one of the most controversial and fascinating ideas: a multiverse born from inflation. We have to be careful here. The word multiverse often sounds like fiction, but in cosmology it can arise from specific mathematical ideas. Some versions of inflation suggest that inflation may not end everywhere at once. In some regions, it stops and forms a universe like the one we observe. In other regions, inflation continues. Elsewhere, more bubble-like regions may form. If such a process occurred, then what we call our universe could be one region inside a much larger inflating structure. Other regions might have different histories. Some might never form galaxies. Some might have different values for physical constants, depending on the model. Some might be completely disconnected from us, not just by distance, but by the structure of space-time itself. This is much more speculative than saying there are more galaxies beyond our horizon. It is not something we can casually present as fact. But it belongs in the conversation, because the question what lies beyond what we can see naturally pushes against the boundary between observed cosmology and theoretical cosmology. The terrifying part is not that the multiverse must be real. We do not know that. The terrifying part is that our observable universe may not be the full arena in which the deepest physics plays out. Everything we call cosmic history might be local. The Big Bang we describe may be the beginning of our observable hot universe, not necessarily the absolute beginning of all reality. The laws we measure may be universal, or they may be the laws of our region. The constants that allow atoms, stars, chemistry, and planets may be fixed everywhere, or they may be one outcome among many possible outcomes in a larger structure we cannot directly inspect. This does not mean scientists are guessing wildly. It means the evidence we have is powerful, but not omnipotent. The observable universe is large enough to make us feel small, yet it may be too small to answer the largest questions with certainty. That contrast is almost absurd. A region tens of billions of light years across may still be a limited sample. This is the scale where human intuition breaks down completely. In normal life, A sample that large feels like everything. In cosmology, it may be the beginning of ignorance. But we should return from speculation to the solid ground of what observation tells us. When astronomers map the universe on large scales, they do not find galaxies scattered randomly, like dust thrown into darkness. They find structure. Galaxies gather in groups and clusters. Clusters connect along filaments. Between the filaments lie vast voids, regions much emptier than the cosmic average. This pattern is called the cosmic web. It grew from tiny variations in the early universe. The cosmic microwave background shows extremely small temperature differences, little density seeds that gravity later amplified. Slightly denser regions attracted more matter. Over billions of years, gas fell into dark matter halos. Stars formed, galaxies assembled, clusters grew, and empty regions became emptier by comparison. This means the structure we see today is connected to conditions in the ancient universe. If the same early pattern continues beyond our horizon, then beyond the visible universe there may be more cosmic web, more filaments, more voids, more galaxy clusters, more dark matter skeletons shaping luminous matter. But there is a subtle limit. We can measure the statistics of the cosmic web inside our observable region. We can ask whether it matches predictions. We can infer that the pattern likely continues. But we cannot point to a specific supercluster beyond the horizon and say, with direct evidence, that it is there. There is no photograph. There is no spectrum. There is no signal. Only a model extending beyond the line where evidence stops. That might sound unsatisfying, but this is how much of science works. We never see the entire object at once. We infer from patterns, laws, and measurements. The difference here is scale. The object is the cosmos, and the unseen portion may be larger than the seen portion by an amount we cannot directly know. This raises a strange question. Could there be something beyond the observable universe that affects us gravitationally, even if we cannot see it? Gravity also propagates at the speed of light, according to general relativity. Changes in gravitational fields do not instantly cross the universe. So a mass distribution beyond our observable horizon cannot simply tug on us in real time, like a hidden planet pulling on a nearby spacecraft. Its gravitational influence is also limited by causality. However, the conditions of the universe we observe could carry imprints from larger-scale initial conditions. If our visible patch formed as part of a much larger pattern, then some features inside it might hint at physics or structure beyond the visible region. Cosmologists have searched for anomalies in the cosmic microwave background, alignments, asymmetries, cold spots, and other features that might be statistical flukes, foreground effects, or clues to something deeper. These studies are difficult because we only have one observable universe to measure. We cannot rerun the cosmos many times to see what patterns are typical. This is called cosmic variance. It means there is an unavoidable uncertainty that comes from having only one sky. You can measure the cosmic microwave background with exquisite precision, but the largest patterns appear only once across our sky. There is no second independent universe beside it for comparison. This limitation is not caused by bad instruments. It is built into the situation. We are trying to understand the statistics of a whole universe from one observable sample. That may be one of the least dramatic but most profound barriers in cosmology. At smaller scales, science can collect many examples. Astronomers can study many stars, many galaxies, many supernovae, many exoplanets. But when it comes to the largest scale universe, there is only one visible cosmic volume. If something unusual appears across that whole volume, we have to ask whether it is a real clue or simply the one roll of the cosmic dice we happen to get. Beyond what we can see, there may be answers that would settle these questions immediately. If we could observe 10 times more universe or 1,000 times more patterns that now look mysterious, might become ordinary, or ordinary assumptions might fail, but we cannot step outside the horizon to check. This is why the edge of the observable universe is not only a physical limit, it is a statistical limit. It controls how much of reality we can sample. And that leads to another important idea. What lies beyond may determine how confident we can ever be about what lies within. Suppose the universe is infinite and statistically uniform. Then our visible region is one patch among endlessly many. It may be representative, or it may contain rare features. If space is truly infinite and matter arrangements repeat under certain assumptions, then there could be other regions with histories similar to ours. Not because of magic, but because endless space allows enormous repetition. But such ideas quickly become speculative and depend on assumptions about infinity, quantum states, and cosmological structure. Suppose instead the universe is finite but far larger than we can see. Then our patch might be part of one grand shape, but we cannot trace the full geometry. Suppose inflation created many disconnected regions. Then our visible universe may be one local outcome, and what lies beyond may be less like distant countries and more like separate domains of cosmic history. Each possibility changes the emotional meaning of the horizon. In an ordinary continuation, the horizon is a curtain over more of the same. In a finite, curved universe, it is a curtain over the universe's hidden shape. In an inflationary multiverse, it is a curtain over an even larger process that may make our cosmos only one branch of a much stranger reality. The problem is that all three can sound enormous, and none can be confirmed by simply staring harder at the darkness. This is why a calm answer to the question must include uncertainty. Not the lazy uncertainty of giving up, the disciplined uncertainty of knowing where evidence ends. We know the universe is expanding. We know light has finite speed. We know the cosmic microwave background comes from an early hot state. We know the observable universe has a horizon. We know the large-scale universe is remarkably uniform across the region we can study. We know distant galaxies show us earlier cosmic times. We know dark energy appears to influence the expansion on large scales. But we do not know the full size of the universe. We do not know whether space is infinite. We do not know whether regions far beyond our horizon are exactly like ours. We do not know whether inflation, if it happened as many models suggest, produced a vast collection of domains beyond direct access. We do not know whether the phrase outside the universe has physical meaning without a larger theory. That set of unknowns is not a failure of astronomy. It is one of astronomy's most honest achievements, the ability to name the boundary. Ancient skywatchers saw stars and imagined a dome. Later, astronomers found planets, then stars like our Sun, then the Milky Way as a galaxy, then galaxies beyond it, then cosmic expansion, then the ancient background radiation. Each discovery made the known universe larger and the old boundary smaller. But the modern boundary is not merely technical, it is woven into causality. That makes it harder to overthrow. A future civilization may see much deeper than we do. It may detect signals we cannot. It may understand quantum gravity, dark energy, inflation, and the earliest universe with a clarity we do not possess. It may know whether our models today were crude sketches or surprisingly close. But even that civilization may still have a horizon. It may still face regions that can never send it information. The universe can become more understood without becoming fully visible. That is a strange kind of progress. The more we learn, the clearer the darkness becomes. Not darkness as ignorance in the simple sense, but darkness as a real feature of the cosmos, a boundary drawn not by lack of curiosity, but by the structure of space-time. This is why the question has such power. What lies beyond the universe we can see? Maybe more galaxies, maybe an infinite continuation, maybe a finite but unbounded space. maybe domains shaped by inflation, maybe nothing we can call beyond in the ordinary sense. But whatever the answer is, our view is not everything. The visible universe is not the universe. It is the part of the universe that has had time to speak to us, and the silence beyond it may be the largest silence that exists. To see why that silence grows even stranger, we have to look at something that feels almost impossible at first: the future horizon. Because the universe is not only hiding regions from us today, it is also preparing to hide some of the regions we can see right now. That may be the most unsettling part of the entire subject. The observable universe is not a fixed museum around us. It changes with time. In one sense, as time passes, light from farther regions has more time to arrive. That sounds as if the visible universe should simply grow forever, revealing more and more of what is outside our present view. But the universe is not only aging, it is expanding, and on the largest scales that expansion appears to be accelerating. This creates two different kinds of horizon. There is the particle horizon, which describes how far we can see because light has had a finite time to travel since the early universe. Then there is the cosmic event horizon, which describes a deeper future limit, places so far away that light emitted from them now will never reach us, no matter how long we wait, if cosmic acceleration continues. That distinction is not obvious at first, but it changes the emotional meaning of distance. Some galaxies are visible to us because we see their ancient light. We can study what they were like billions of years ago. Yet the light they emit today may never arrive here. Their young image is inside our past, while their present is already beyond our future. A galaxy can be seen and unreachable at the same time. That sounds contradictory, until you remember that looking across the universe is looking into history. We are not seeing distant galaxies as current neighbors. We are receiving old mail from a place whose later messages may be lost forever. Imagine standing beside a road while a traveler walks away into fog. A letter sent early reaches you. Another letter sent later might not, because the road stretches faster than the traveler can close the gap with the message. You still know the traveler existed. You may even know where they once were, but their ongoing story is gone from your future. Cosmic acceleration gives the universe a similar cruelty. It does not only place unknown regions beyond the present horizon, it can turn known regions into fading records. Over extremely long times, distant galaxies outside our gravitationally bound neighborhood will become more redshifted, dimmer, and harder to detect. Their light will stretch until it becomes too weak and too long in wavelength for any practical observer to see. The universe of the far future may look emptier, not because galaxies have vanished from existence, but because expansion has carried their signals away from access. A civilization born very far in the future might not see the same cosmic evidence we see tonight. It might live in a merged local galaxy, surrounded by darkness. It might have no easy view of distant galaxies rushing away, no clear map of the cosmic web, and perhaps a much harder path to discovering the Big Bang. The evidence that seems normal to modern cosmology could become hidden by time itself. This gives our era a strange privilege. We live late enough for galaxies, stars, heavy elements, rocky planets, and life to exist. But we also live early enough that the distant universe is still visible. We can still see deep fields. We can still detect the cosmic microwave background. We can still measure galaxies beyond our local group. We can still read the expansion history written into ancient light. The universe is not fully open to us, but it is more open now than it may be to observers in the far future. That turns the question beyond the visible universe into a race against cosmic time, not because humans can physically reach the edge, but because the light we use to understand the universe is fading into deeper redshift. Astronomy is not only looking outward, it is collecting evidence before the evidence becomes unreachable. This is why the cosmic horizon is not just a line at the end of a map. It is a moving relationship between light, expansion, and time. And it means the invisible part of the universe is not one simple category. There are regions we cannot see yet, because their light has not arrived. There are regions we may never see, because expansion prevents their signals from reaching us. There are earlier times hidden from ordinary light because the universe was opaque. There are possible global shapes too large for our visible patch to reveal. There are theoretical domains that may exist in some models but remain beyond direct testing. All of these get mixed together when people ask what lies outside the observable universe, but they are not the same mystery. A good answer has to separate them. The first mystery is distance. More space may exist beyond our current light horizon. The second is time. We see ancient versions of distant regions, not their present reality. The third is physics. The early universe blocks electromagnetic sight before the cosmic microwave background. The fourth is geometry. The total shape and size of space may be larger than our sample can prove. The fifth is theory. Inflation or other high-energy processes may imply a much larger structure than the one our telescopes can inspect. When these layers are separated, the question becomes clearer and more frightening. It is not just that we cannot see far enough. It is that seeing itself is made from rules that do not allow a complete picture. This is a difficult idea, because human exploration is usually built on the assumption that limits are temporary. A mountain can be climbed, an ocean can be crossed, a planet can be reached with enough fuel, patience, and engineering. Even a black hole can be studied from outside by its effect on light and matter. But some cosmic limits are not like mountains. No matter how advanced a telescope becomes, it cannot receive light from a source whose light never arrives. No matter how patient a civilization becomes, it cannot watch the current day of a galaxy whose present signals are forever outside its event horizon. No matter how intelligent an observer becomes, it cannot compare its cosmic patch to regions causally disconnected from it, unless those regions leave some indirect trace inside the patch. There may be truths that exist, but cannot become observations. That sentence sounds almost unscientific, but it is not. Science does not require every truth to be accessible. It requires that claims be tied to evidence. If a region is beyond all possible evidence, then science can discuss models and implications, but it cannot treat the unseen region as measured fact. This is why responsible cosmology is both bold and restrained. It builds equations for the whole universe, yet admits that the data arrive from a finite window. It imagines inflation, quantum beginnings, curved topologies, and cosmic futures, yet returns again and again to maps, spectra, background radiation, redshifts, and gravitational patterns. The invisible universe is not an excuse to invent anything. It is a reminder that even the largest scientific story is still anchored to what the cosmos allows us to know. Now, imagine moving outward in thought, not in a spacecraft, but in scale. Begin with Earth at night. Cities glow on the dark side. The moon pulls tides across oceans. The sun lies 8 light minutes away, ordinary and blinding from our perspective. Farther out, the planets become small worlds spaced by millions and billions of kilometers. Then, the sun becomes one star among many. The nearest stars sit years away at light speed. The Milky Way stretches across 100,000 light-years. Andromeda waits millions of light-years away. Clusters gather tens and hundreds of millions of light-years beyond that. Then, the scale stops being visual. It becomes statistical. You no longer imagine individual stars. You imagine maps of galaxies, each point a whole stellar city. Then the maps become filaments and voids. Then the filaments become a pattern inside an observable sphere. Then that sphere becomes one patch, whose outside may be larger than anything inside the map. At that level, the word beyond becomes almost too small. Beyond might mean a galaxy whose ancient light has not reached us. Beyond might mean a region that will never communicate with us. Beyond might mean a part of the same universe that shares our laws but not our sky. Beyond might mean a domain separated by inflation. Beyond might mean the answer to whether the universe is finite, infinite, curved, flat, repeating, or open without end. Each meaning is different, and none can be reduced to a simple picture of a wall with something behind it. This is why the most honest thumbnail for the subject might not show a spacecraft reaching an edge. It might show a bright island of galaxies fading into a blackness that is not empty, only inaccessible. Because that is closer to the truth. The visible universe is an island of information, not an island in space, but an island in the sea of possible signals. Around it lies more than darkness. Around it lies uncertainty shaped by physics. And yet, the fact that we can know even this much is astonishing. From one small planet, using glass, mirrors, detectors, mathematics and patient observation, humans have measured the age of the universe, mapped ancient radiation, inferred invisible matter, detected cosmic acceleration, and estimated the size of the region from which light has reached us. That does not make the horizon disappear, but it means the horizon is no longer a blank superstition. We know why it is there. We know some of what it hides. We know why some of it may stay hidden forever. The question now becomes more precise. If, beyond the observable universe is probably not an edge, and probably not a simple outside, then what are the realistic possibilities for the larger cosmos? To answer that, we have to move from what telescopes directly show to what the shape of space may allow. And that begins with a quiet but enormous possibility. The universe may be far larger than the visible part, and still almost perfectly ordinary. If that is true, then beyond our horizon there is no dramatic wall, no sudden change in the laws of physics, and no final border glowing in the dark. There is simply more cosmic web, more galaxies we will never name, more stars whose light will never touch our instruments, more planets forming around suns that are not even rumors in our sky. Some of those worlds, if they exist, may have oceans. Some may be frozen, some may be burned by their stars, some may be lifeless rocks. Some may orbit calmly in galaxies beyond the reach of every signal we can ever receive. They would not be imaginary to themselves. They would only be invisible to us. That is a different kind of terror from destruction. It is not the fear of something coming for Earth. It is the fear that reality is larger than contact, larger than evidence, larger than any story a single observer can assemble. The universe may not be hiding monsters beyond the horizon. It may be hiding ordinary places. And ordinary places, multiplied beyond sight forever, may be stranger than any monster. Because a monster at least enters the story. An unreachable world never does. It can exist, change, orbit, freeze, burn, and die without becoming part of our universe of experience. It may have a sky full of galaxies we cannot see, and from there, our entire observable universe may be outside their horizon. Their astronomers, if any ever existed, would build their own maps. Their cosmic microwave background would surround them. Their deepest fields would point into their own ancient past. They might ask, what lies beyond the universe they can see? And we would be part of their answer, yet forever absent from their evidence. This is the strange symmetry of cosmic horizons. We are not only limited observers, we are also hidden from others. The horizon does not just take the universe away from us. It takes us away from the universe. That realization is colder than the image of a dark edge. It means that beyond what we can see may be filled with histories that can never join ours, not because they are unreal, but because the universe is too large and too fast changing for every story to meet. And this is only the first half of the mystery, because once we accept that more universe may lie beyond our horizon, the next question is whether that hidden universe must follow the same pattern everywhere. Maybe it does. Maybe it does not. The evidence inside our visible region gives us confidence, but not omniscience. The cosmic microwave background is smooth, but not perfectly smooth. The universe is uniform on large scales, but local structure varies. Inflation may have stretched space enormously, but the details of inflation remain uncertain. Dark energy may continue accelerating expansion, but its deepest nature remains unknown. Every answer opens another door. If space is infinite, what does infinity contain? If space is finite, what is its global shape? If inflation created regions beyond reach, are they still part of our universe in any meaningful observational sense? If the laws of physics are the same everywhere, why these laws? If they are not the same everywhere, why do we live in the region we do? These are not questions a telescope alone can finish. They require theory, measurement, restraint, and imagination disciplined by evidence. So far, the strongest answer remains simple but immense. The universe we can see is not all there is, and the part beyond it is probably not a boundary but an extension, a hidden continuation, or a larger structure whose full form is beyond our horizon. But this answer leads directly into the darker side of the story. Because if there is more universe beyond our sight, then there may also be more time beyond our sight. Future versions of distant places that will never be seen, present-day galaxies already lost behind expansion, and a cosmic map that becomes poorer the longer the universe accelerates. The hidden universe is not only beyond us in space, it is beyond us in time. And that is where the second half of this journey must go. It begins with a strange fact about distance. When we look far enough away, we are not looking at where the universe is now. We are looking at where parts of it used to be. A galaxy 10 billion light-years away is not being seen as it exists tonight. Its light began traveling when the universe was younger, when many stars had not yet formed, when the Milky Way was still building itself through collisions and gas flows, and when Earth did not yet exist as a finished world. That means the visible universe is not a live map. It is a layered record. Nearby space is almost present. Farther space is older. The most distant light is the youngest view we can receive. And beyond that limit, the hidden universe is not only hidden because it is far away. It is hidden because its light has not had enough time to arrive, or because expansion has changed the rules before the message could reach us. This makes the question deeper than it first sounds. What lies beyond the universe we can see is not simply another region behind a cosmic curtain. It may be a region whose present moment is already separated from us forever. Imagine standing in a dark room with a single lamp at your feet. The lamp does not reveal the whole building. It only reveals the dust, walls, and objects close enough for its light to touch. But the universe is stranger than that. In a normal building, light from a distant room could eventually arrive if you waited long enough. In an accelerating universe, there are rooms whose light may never reach you, no matter how patiently you wait. The darkness is not just distance. It is a horizon created by time, expansion, and the finite speed of light. This is where the hidden universe becomes terrifying. Not because there is necessarily something monstrous beyond the edge, but because the edge itself is moving through history. The universe is not giving us more and more of itself forever. In one sense, telescopes improve. Our instruments get larger, colder, sharper, and more sensitive. We learn to see infrared light that human eyes cannot see. We build detectors for radio waves, X-rays, neutrinos, and gravitational waves. We compare patterns in the cosmic microwave background with galaxy surveys across billions of light years. But in another sense, the universe is slowly taking information away. Distant galaxies are not simply sitting still while we try to observe them. Space between galaxy clusters is expanding, and because that expansion is accelerating, there is a cosmic event horizon, a limit beyond which events occurring now will never be visible to us in the future. A galaxy may be visible in an old photograph of its past, while its present-day light is already beyond reach. That is a very different kind of disappearance. If a ship could leave Earth tonight and travel outward, it would not be chasing a fixed wall. It would be trying to cross a universe whose most distant reachable regions depend on how fast the ship moves, how long it survives, and how space itself changes during the journey. Light is the fastest messenger we know, and even light loses access to parts of the cosmos as accelerated expansion stretches distances faster than new signals can close them. This does not mean galaxies are flying through space faster than light in the local sense. Locally, the ordinary rules still hold. A galaxy beside you does not outrun a beam of light passing nearby. The problem is the fabric between enormous regions. At large enough scales, the distance itself grows. That growth is what changes the future. Think of a distant galaxy that we can still see because it emitted light billions of years ago. The light entering our telescope tonight may show a young, blue, active system filled with star formation. But the galaxy itself has aged. Its stars have moved. Its gas has changed. It may have collided with neighbors. It may contain black holes that have grown larger, supernova remnants that have cooled, and planets that have formed around stars we will never see at their present age. The galaxy we receive is real, but it is not current. The hidden universe, then, includes the present-day version of things whose past is still visible. This is one of the most unsettling ideas in cosmology. We do not merely lack information about distant places, we are separated from their now. The farther we look, the more the word now loses its ordinary meaning. On Earth, we can pretend that the world shares one present. A city across the ocean is happening at nearly the same time as the room around you. Signals move quickly enough for daily life to feel connected. But on cosmic scales, simultaneous becomes fragile. A star exploding in a remote galaxy, a planet forming around a distant sun, or a civilization turning its telescopes outward, may all belong to a present we cannot join. Beyond the visible universe, this separation becomes complete. Not delayed, complete. And this is why the edge of what we see is not only a scientific boundary, it is a boundary of participation. We cannot exchange light with much of what exists. We cannot receive its history after a certain point. We cannot influence it, warn it, meet it, or even know whether its galaxies resemble ours. If the universe beyond our horizon is filled with ordinary galaxies, then countless stars may be burning there tonight, without ever becoming part of our sky. They are not dim, they are disconnected. That is the first answer to what lies beyond what we can see. More history than we can receive. And the second answer is even stranger. There may be observers beyond our horizon who are asking the same question from somewhere we will never reach. From their position, the observable universe would not be the same sphere as ours. It would overlap with ours in some regions if they were close enough on cosmic scales, but farther away. Their cosmic bubble would contain galaxies we cannot see and omit galaxies that are central to our own map. Their cosmic microwave background would come from a different shell around them. Their surveys would trace a different section of the cosmic web. Their local sky would include structures that, to us, are permanently beyond the edge. This means the observable universe is not a unique object. It is an address-based view. Earth has one cosmic horizon. Another galaxy has another. A civilization far beyond our observable boundary, if it exists, could live inside a universe that feels just as centered as ours does from here. Their astronomers could measure expansion, study relic radiation, map galaxy clusters, and calculate limits. They might conclude, correctly from their own location, that they occupy the center of their observable universe. And they would not be wrong. Every observer sits at the center of the sphere they can see, not because the universe is built around them, but because light reaches them from all directions over a finite time. This is easy to say and difficult to feel. Human minds are used to maps with edges. If there is a circle, we want to stand outside it and look at the whole shape. But the observable universe does not work like a country on paper. Its edge is not a coastline. There is no known cosmic cliff where galaxies end and nothing begins. The edge is a limit in the information that can reach one place. So if we ask what is beyond it, one careful answer is regions that might have their own observable universes, centered on other points, with their own horizons and their own unreachable beyonds. This creates a universe that cannot be captured from any single seat. No matter where you place a telescope, you only get a bubble. A larger civilization spread across many galaxies would have a larger combined view. It could compare skies from different locations and reduce some uncertainties that trap us on Earth. It could look at the cosmic microwave background from different angles. It could map structures invisible from our neighborhood. It could test whether large-scale patterns continue beyond our present limits. But even a civilization spread across the local group would still be small compared with the total cosmic horizon. And as expansion accelerates, moving observers apart does not guarantee unlimited knowledge. There are limits that no network can beat if its stations remain inside a region that becomes increasingly isolated. The universe allows local knowledge to grow. It does not necessarily allow total knowledge. This matters because our biggest conclusions about the cosmos come from only one observable patch. We assume, based on evidence, that the universe is broadly the same in all directions on very large scales. This idea is called the cosmological principle. It has served science extremely well. The cosmic microwave background is smoothed to a remarkable degree after tiny fluctuations are removed. Galaxy surveys reveal a web-like structure that becomes statistically more uniform as the scale grows. The laws of physics appear to work consistently across the regions we can measure. But there is still a quiet limitation. We have one sky. We cannot step outside the observable universe and inspect whether our patch is typical. We cannot look at 10,000 separate cosmic horizons and compare their average properties. We cannot prove from direct observation that the region beyond our boundary behaves exactly like ours. We can infer, we can model. We can test every visible clue, but we cannot perform the ultimate survey. This is called cosmic variance in a broad sense, the fact that our observable universe is one sample. For many measurements, especially patterns on the largest scales, there is an unavoidable uncertainty because the universe gives us only a limited number of independent regions to study. Imagine trying to understand an entire forest from one clearing. If the clearing contains many trees, many insects, soil, roots, leaves, and weather patterns, you can learn a great deal. You can build excellent botany. You can discover photosynthesis, ecology, and the way seasons change growth. But if someone asks whether the forest is infinite, whether another valley contains the same species, or whether a strange structure lies beyond the hills, the clearing can only tell you so much. The observable universe is our clearing. The cosmic horizon is the hills. Beyond them, the forest may continue in the same way. That is the simplest assumption, and it may be correct. But the fact that we cannot walk to the ridge changes the kind of answer we can claim. This is where speculation begins. But it must begin carefully. The most conservative picture says that beyond our observable universe, there is simply more universe like ours. More galaxies, more clusters, more voids, more dark matter, more radiation, more cosmic web extending far beyond the region light has had time to show us. In this view, nothing magical happens at the edge. There is no wall, no outside surface, no sudden change from existence to non-existence. The horizon is an observational limit, not a physical ending. This picture is powerful because it fits what we already see. The visible universe does not appear to become stranger as we approach the horizon in a way that suggests a nearby edge. We see older stages of cosmic history, not a final boundary. The cosmic microwave background comes from all directions with a smoothness that points toward an early universe far larger than the patch that later became visible to us. Inflation, if it happened, would naturally make the total universe much bigger than our observable region, possibly enormously bigger. In that conservative view, what lies beyond is not a different realm. It is more of the same cosmic story. But more of the same can still be overwhelming. If the universe is infinite, or merely far larger than our horizon, then the visible cosmos is not the main stage. It is a local volume. All the galaxies we have ever photographed, all the quasars, all the clusters, all the dark matter filaments, all the empty voids, all the stars in every image from Hubble and Webb, all of it may be a tiny portion of a structure without any human-sized comparison. The terror here is not that beyond the horizon is strange. It is that it may be ordinary and still endless. An endless ordinary universe is difficult to hold in the mind. It means that the Milky Way is not merely one galaxy among many in our visible sphere. It may be one galaxy among a number so large that even the word many fails. The observable universe already contains hundreds of billions of galaxies, perhaps more, depending on how small and faint one counts them. If the total universe continues far beyond that, then even our grandest maps are local sketches. There may be regions where the cosmic web stretches in patterns we will never name. There may be clusters larger than any visible supercluster. There may be voids so wide that no light from their far walls will ever enter our telescopes. There may be planets with oceans, moons with ice shells, stars with civilizations, and dead worlds orbiting red dwarfs, all outside the future light cone of Earth. Not hidden because they are secret. Hidden because the universe is larger than communication. This possibility can feel peaceful or terrifying depending on how it is held. Peaceful, because it means our horizon is not a prison wall around existence. Terrifying, because it means reality is not obligated to be available to awareness. Existence may exceed observation by an unimaginable margin. And then there is the question of shape. The universe may be infinite, but it does not have to be. A finite universe can still have no edge, just as the surface of Earth has a finite area but no edge where the ground simply stops. If you travel far enough in one direction on Earth, you do not fall from the map. You return from another direction. Space itself could, in principle, have a topology that wraps around in a higher dimensional way, though not like a sphere sitting inside ordinary space that we could view from outside. If the universe has such a shape, then beyond the observable universe might not be endless new territory. It could be connected to regions that, in a complete map, loop back in ways that are almost impossible to visualize. Astronomers have looked for signs of this. One idea is that if space wraps around on a scale not much larger than what we can see, patterns in the cosmic microwave background might repeat. Circles of matching temperature fluctuations could appear in different parts of the sky, like the same ancient light, seen along different paths. So far, there is no clear evidence that the observable universe wraps around on a scale small enough for us to detect. That does not prove space is infinite. It tells us that if space is finite in this way, its full size is likely larger than the region we can test, or its topology is not easily revealed by current data. This is another case where the hidden universe escapes by scale, not because the idea is unscientific, because the evidence may lie beyond the portion of the universe available to us. The difference between an infinite universe and a finite but enormous one is not just philosophical. It changes the meaning of beyond. In an infinite universe, beyond our horizon may continue without end. In a finite wrapped universe, beyond may eventually lead back to the same cosmic structure from another direction, though across distances and histories we cannot observe. In a universe born from inflation, beyond may include regions that share our origin, but are so separated by expansion that they function like independent cosmic worlds. Each possibility is humbling in a different way. An infinite universe makes our observable patch small by comparison with everything. A finite but unbounded universe makes the concept of an edge misleading. An inflationary universe makes our region one cooled pocket inside a much larger process. None of these pictures gives us a simple wall with an answer written on the other side. The universe is not hiding a door, it is hiding the map. This becomes even more complex when we consider inflation. In many modern cosmological models, the early universe underwent a period of incredibly rapid expansion. A tiny region could have been stretched to vast size, smoothing out space and making the universe appear nearly flat across our observable patch. Inflation also helps explain why regions of the cosmic microwave background on opposite sides of the sky have nearly the same temperature, even though, without such an early process, they would not have had time to exchange information. If inflation happened, then the universe beyond what we see may be far larger than the observable region. But some versions of inflation go further. They suggest that inflation may not end everywhere at once. In some regions, it stops and forms a universe like ours, filled with particles, radiation, galaxies, and later stars. In other regions, inflation continues. Elsewhere, it stops again, creating another bubble or pocket. This is the broad idea behind eternal inflation. Here, we must be careful. This is not the same as saying science has discovered another universe. We have not photographed a neighboring bubble. We have not received a signal from outside our cosmic region. Eternal inflation is a theoretical possibility arising from certain models, not an observed landscape we can tour. But if such a picture is correct, then what lies beyond our observable universe may not simply be more galaxies like ours. At unimaginably larger scales, there could be other regions where inflation ended differently, perhaps with different physical conditions. Some might have no galaxies. Some might have different particle properties. Some might expand too quickly for structure. Some might collapse. Some might be rich, cold, empty, or violently unstable. This is where the word universe becomes slippery. Traditionally, the universe means everything that exists, all space, time, matter, energy, and the laws governing them. In that sense, there cannot be something outside the universe, because the word includes everything. But in cosmology, people sometimes use universe to mean our observable region, or our connected post-inflationary patch. Then the word multiverse appears to describe a larger structure, containing many such patches. The danger is that language can make the idea sound more concrete than the evidence. So a disciplined script must say this plainly: the multiverse is a possibility, not a confirmed destination. But it is a possibility born from serious attempts to understand the beginning. And it changes how we imagine beyond. If the hidden universe is only more of the same, then beyond the horizon lies unreachable continuity. If the hidden universe includes inflationary domains unlike ours, then beyond may include parts of reality where our familiar assumptions break down. Not fantasy worlds, but physically distinct regions produced by different conditions in an early cosmic process. That is much harder to test. It may be permanently harder to test. And the terrifying part is not that such places would be dangerous to us. We cannot travel there. They would not be next door in any ordinary sense. The terrifying part is that the deepest structure of reality might include more than any observer inside one region can ever prove from direct contact. We may be living inside a local answer, not the final one. Even within the more conservative view, there is a hidden violence in cosmic scale. The universe beyond our sight may contain the same kinds of objects we study here, but the same kinds are already extreme enough. There may be quasars brighter than those in our maps. There may be black holes larger than the largest we have measured. There may be galaxy clusters still forming along filaments we will never chart. There may be cosmic voids that alter the motion of entire regions through gravity. There may be ancient light from events that occurred, crossed part of the cosmos, and then vanished forever from all possible contact with us. No monster is needed. Ordinary cosmology is strange enough. A star beyond our horizon could explode tonight. Its neutrinos could cross its local galaxies. Its shockwave could seed future stars in its region. Planets could be sterilized or enriched by the heavy elements it sends into space. And none of that would ever become news here. There would be no afterglow in our sky, no archive image, no measurement, no delayed signal for our descendants. The event would be real. It would just be absent from our universe of evidence. This distinction matters. Science is built on evidence, and evidence must arrive somehow. It can come as light, particles, gravitational waves, chemical traces, motion, temperature, pattern, or effect. But if no effect can reach us, then the event may exist outside our possible science. Not because science is weak, but because science respects contact with reality. There are things that may be real, but unreachable. That sentence must be handled carefully. It should not be used as permission to believe anything. It is not an excuse for inventing whatever story sounds dramatic. It is a reminder that the observable universe is not identical to the total universe. Responsible imagination begins exactly there. It asks what our best-tested theories imply, then marks where certainty ends. So, what can we say with confidence? We can say that the observable universe is limited by the age of the cosmos, the finite speed of light, and cosmic expansion. We can say that the boundary we see is not a physical wall. We can say that the cosmic microwave background is not the edge of space, but the earliest light that could travel freely after the universe became transparent. We can say that there are probably regions beyond our current view, because inflation and the smoothness of the universe strongly suggest that our observable patch is not the full extent of reality. We can say that accelerated expansion creates future horizons, so some light emitted now in distant regions will never arrive here. We can say that the total universe may be infinite, or finite, but larger than what we can measure. And current observations do not settle the question fully. And we can say that if other observers exist far beyond our horizon, their view of the universe would be different from ours, centered on their own location, bounded by their own light cone. That is already a profound answer. But it is not the answer people usually want. People often want the other side to be a place. They imagine crossing the edge and finding a new realm, a blank white border, a cosmic wall, a sea outside space, or another universe sitting beyond ours like an island beyond an ocean. The real answer is subtler. There may be no outside in the ordinary sense. The universe is not known to be expanding into a pre-existing emptiness. Expansion means distances within space grow. Galaxies that are not gravitationally bound drift farther apart because the metric of space changes. The common image of a balloon can help, but it also misleads. The surface of the balloon expands, but the balloon exists inside a room. The universe, as far as the model is concerned, does not need a room. It is not necessarily expanding into something. It is expanding. That difference is hard to visualize because every everyday expansion happens inside a larger container. Smoke spreads into air. Water fills a cup. A crowd moves into a square. But space-time is not an object inside a room in the same simple way. Asking what it expands into may be like asking what is north of the North Pole. The question uses words that work locally, then pushes them beyond their domain. This does not mean the question is foolish. It means the answer may require abandoning the picture that produced the question. When we ask what lies beyond the universe we can see, we must separate two questions that often get mixed together. First, what lies beyond the observable horizon? Second, what lies outside the entire universe? The first question has scientific answers and careful possibilities. Beyond our horizon may be more of the universe, hidden by distance and expansion. The second question is much more difficult. If the universe means all of space and time, outside may have no physical meaning. If our universe is one region in a larger multiverse, outside could mean something in a broader structure. But that moves into theoretical territory that is not directly observed. So the strongest answer is layered. Beyond the visible universe, probably more universe. Beyond the total universe, perhaps no beyond at all. Beyond our current theories, questions we have not yet learned how to ask. That layered answer may not be as simple as a wall or a portal, but it is more powerful. It tells us that the boundary is partly in space, partly in time, partly in observation, and partly in language. The horizon is not one thing. It is several limits, wearing the same name. There is the particle horizon, the limit of how far light has traveled to us since the beginning. There is the surface of last scattering, the glowing shell of the cosmic microwave background, beyond which the earlier universe was opaque to light. There is the event horizon, the future limit beyond which signals emitted now will never reach us. There are technological horizons, faintness, dust, detector sensitivity, foreground noise, and the ability to distinguish one interpretation from another. There are theoretical horizons, places where our equations remain incomplete, especially when gravity and quantum physics must both be understood. And there are philosophical horizons, the boundary between what can be known, what can be inferred, and what may remain forever outside evidence. When all these horizons overlap, the result feels like a single edge. But it is not a wall. It is a stack of limitations. This is why the hidden universe is such a powerful documentary subject. It is not just remote. It forces us to ask what kind of creatures we are. We are beings who evolved under a sky where the farthest visible objects were nearby stars. Then we learned that those stars are suns. Then we learned that the Milky Way is a galaxy. Then we learned that galaxies fill space. Then we learned that the galaxies we see are not the whole, and that the light we collect is a time capsule from a universe still changing beyond the reach of our maps. Every expansion of knowledge made the universe larger, but it also made our boundary clearer. That is the strange pattern of cosmology. Understanding does not always remove mystery. Sometimes it defines mystery with greater precision. The ancient question was simple: where does the sky end? The modern version is sharper. What information can ever enter our world line, and what remains outside it because of the causal structure of space-time? That is a far colder question. It does not ask whether humans are clever enough. It asks whether cleverness matters when the signal cannot arrive. This is where the future of astronomy becomes bittersweet. In the near future, telescopes may reveal galaxies closer to the cosmic dawn than ever before. Infrared observatories can see light stretched by expansion from early stars and galaxies. Gravitational wave detectors may one day probe events invisible to ordinary telescopes. Neutrino astronomy may grow stronger. 21-centimeter cosmology may map the ancient hydrogen fog before and during the first stars. Better surveys will chart dark matter through lensing. and measure the large-scale structure of the universe with increasing precision. Each step will push the practical boundary outward, but none will erase the fundamental horizon. Even the best telescope cannot receive light that never arrives. Even the most patient civilization cannot wait its way past an event horizon created by accelerated expansion. Even perfect instruments cannot turn one observable patch into an outside view of the whole. Future science may answer many questions that seem impossible today. It may learn whether inflation happened and what kind. It may discover signatures of primordial gravitational waves. It may map the curvature of space more precisely. It may constrain the shape of the universe. It may reveal whether dark energy behaves like a cosmological constant or changes over time. It may find that our current model needs revision. But whatever replaces our model must still deal with evidence, and evidence reaches observers through channels. If a region can never send a channel to us, it cannot be observed by us in the ordinary sense. That is not a weakness of one era's technology. It is built into the structure of the problem. This is also why the phrase "the universe we can see" is not childish. It is one of the deepest phrases in science. It admits that seeing is not everything, but it also admits that seeing, measuring, and receiving signals are how science anchors itself. The universe we can see is not the whole of existence, but it is the part that has entered relationship with us. Everything else is beyond relationship unless it left an imprint we can detect. Inflation may have left imprints. The early universe may have left statistical patterns. Quantum fluctuations may have become the seeds of galaxies. Dark matter may reveal itself through gravity. Dark energy may reveal itself through expansion history. The hidden universe, if it exists beyond our direct view, may still shape what we observe indirectly if it affected the conditions of our patch. That is the hope. The hidden may not be totally silent if it helped write the visible, but there is a limit to indirect evidence. A footprint in sand can tell you that something passed by. It may reveal weight, direction, and timing. It may not reveal the entire landscape from which the traveler came. Cosmology reads footprints in ancient light. It studies the temperature pattern of the CMB, the distribution of galaxies, the abundance of elements, the way light bends around mass, and the expansion rate across cosmic time. From these traces, we reconstruct a history, but beyond the horizon, the full territory remains unseen. That is the difference between inference and contact. The hidden universe may leave fingerprints in the earliest visible radiation. It may affect the shape of space. It may be required by inflation. It may be suggested by the flatness and smoothness of what we observe. Yet the regions themselves remain outside the direct image. That is why any honest answer must end with both confidence and humility. Confidence, because modern cosmology is not guessing in the dark. It is built on measurements, redshifts, supernova, galaxy surveys, background radiation, gravitational lensing, element abundances, and more. Humility, because the largest question points beyond the largest available evidence. What lies beyond the universe we can see may be more stars, more galaxies, more voids, more history, more cosmic structure, and perhaps even regions produced by physics we only partly understand. But it is not waiting for us like a nearby continent. It is separated from us by the rules that make observation possible in the first place. If that sounds abstract, bring it back to a single photon. Imagine a photon released by a young star beyond our observable horizon. It moves at light speed, not lazily, not weakly, but as fast as anything can move through space. It travels through intergalactic darkness. It passes dust, magnetic fields, faint gas, and the gravity of unseen matter. It carries a message about the star that created it. But while it travels, space expands. The distance between that photon and future Earth may not shrink enough. The universe may stretch the route faster than the photon can overcome at cosmic scales. Not because the photon is slow, because the road is changing. That photon may never enter a human telescope. It may never enter any telescope built by descendants of Earth. It may remain forever outside our story. Now multiply that by galaxies. Multiply it by all the events happening now beyond our horizon. That is the hidden universe. A vast collection of real things whose messages cannot become part of our evidence. This is why the question is not merely scientific. It touches something emotional, even if the science itself remains calm. Humans are used to believing that unknown places can eventually be reached. Oceans were crossed. Mountains were climbed. Poles were visited. The far side of the moon was photographed. Planets were mapped by probes. Even Pluto, once a distant point, became a world with mountains, plains, haze, and surface features. Again and again, unknown became known. But cosmology reveals a different category. Unknowns that may remain unknown, not because they are difficult, but because they are causally unavailable. That is a harder kind of mystery. It does not invite conquest, it invites acceptance. And yet acceptance does not mean giving up. It means understanding the scale of the map. We can still learn more than any previous generation imagined. We can still push the early universe into clearer focus. We can still measure dark energy more precisely. We can still search for curvature, topology, primordial waves, and the signatures of first light. We can still explore the part of the universe that has entered our sky with astonishing depth. The visible universe is finite, but it is not small. It contains enough mystery for many civilizations. The fact that there is more beyond it does not make the visible part worthless. It makes it precious. It is the accessible page of a book that may have no final page, or whose final pages are sealed by the physics of the story itself. And this page is extraordinary. It contains Earth. It contains the Sun. It contains the Milky Way, Andromeda, the Local Group, galaxy clusters, cosmic voids, quasars, relic radiation, dark matter, black holes, neutron stars, planets, dust, ice, chemistry, and the fragile ability of matter to become aware of the universe that made it. The visible patch may be small compared with everything, but it is not insignificant. It is the only part from which this question can be asked by us. This gives the ending a different feeling. The question was, what lies beyond the universe we can see? The most honest answer is not one sentence. Beyond the visible edge, there is likely more universe, more space, more galaxies, more dark matter, more ancient light still traveling, and more events whose present we cannot access. Beyond our future reach, there are regions carried away by accelerated expansion, places whose final chapters will never enter our records. Beyond the cosmic microwave background, there is an earlier universe hidden by the opacity of its own youth, accessible only through indirect traces. Beyond our current theories, there may be inflationary domains, unknown topology, or structures larger than the region we can observe. Beyond the total universe, if that phrase even has meaning, there may be no outside at all. And beyond all of this, there is the deepest boundary, the difference between reality and the part of reality that can ever be known from here. That may be the true other side. Not a wall, not a void, not a place where the universe ends, but a limit where existence continues without becoming visible. For a species that learned to survive by seeing, mapping, naming, and crossing horizons, that is almost unbearable. And maybe that is why the hidden universe feels so powerful. It reminds us that the cosmos is not designed around human curiosity. It does not owe us the whole picture. It allows us a view, and that view is astonishing, but it does not promise completeness. Still, there is something beautiful in that. because the same laws that hide the farthest regions are the laws that let us understand why they are hidden. The same light speed that limits our reach lets us reconstruct time. The same expansion that carries galaxies away lets us measure cosmic history. The same background radiation that blocks direct sight into earlier times gives us the oldest image of the universe we have. The boundary is not only a denial, it is also a clue. The universe we can see is a message from the universe we cannot. Every redshifted galaxy, every faint microwave fluctuation, every gravitational lens, every ancient quasar is part of that message. None of them shows the whole. Together, they tell us that the whole is larger than the visible, older in its hidden histories, and stranger in its structure than our eyes alone could ever guess. So when we ask what lies beyond, perhaps the answer is not only out there, it is also in the way the visible universe carries scars of a greater reality. The edge of sight is not the edge of existence. It is the edge of our conversation with it. And beyond that edge, the universe may continue in silence. Ordinary, infinite, wrapped, inflating, unreachable, or something our present language cannot yet hold. We may never know which answer is complete, but we know enough to understand the scale of the mystery. There is one more way to understand the hidden universe, and it begins not at the edge of our telescopes, but in the far future of our own sky. If the universe continues accelerating in the way current evidence suggests, the night sky will not always tell the same story. The distant galaxies that fill our deepest images will become harder to observe. Their light will stretch to longer wavelengths. Their apparent motion will slow. Their signals will fade into the background until, for practical purposes, they disappear from view. This disappearance will not happen tomorrow. It will not happen on the timescale of human history. But over immense spans of cosmic time, observers living in the merged remains of the Milky Way and Andromeda may look outward and see a much emptier universe. Their local galaxy may still contain stars, planets, remnants, dust, black holes, and perhaps life. But the distant cosmic web could be gone from the visible sky, carried beyond detection by accelerated expansion. Imagine a civilization born in that age. They might build telescopes larger than anything we can imagine. They might understand physics with a precision far beyond ours. They might live in a galaxy formed by the collision of the Milky Way and Andromeda, under skies where ancient star streams wrap around a giant merged structure. And still, they might not see the evidence that taught us the universe is expanding. They might not see the rich population of distant galaxies that fills our current observations. They might not have easy access to the cosmic microwave background if it has been stretched to wavelengths too long and faint to separate from local noise. To them, the universe might look like an island of stars surrounded by darkness. This is one of the strangest reversals in cosmic history. We often think later civilizations will always know more than earlier ones. In technology, that may be true, but in cosmology, timing matters. There are facts about the universe that are easier to discover during certain eras than others. We live after the first stars and galaxies formed, so the universe is lit. We live before distant galaxies vanish beyond practical detection, so the large-scale structure is still visible. We live long after the cosmic microwave background was released, but early enough that it is still measurable as a cool glow across the sky. Our age is not only a moment in the universe, it is an observational window. The hidden universe therefore has a future dimension. Some things are hidden from us now because their light has not reached us. Other things will become hidden from future observers because their light will fade beyond recovery. The visible universe is not a permanent gift. It is a temporary arrangement between cosmic history and the observers who happen to exist inside it. This changes the meaning of our maps. Every deep field image is not just a photograph of distant galaxies. It is a rescue of information before time makes it harder to receive. Every measurement of the cosmic microwave background is not only a study of the early universe, it is a record from an era when the ancient glow remains accessible. Every galaxy survey is a map of a universe that future beings may not be able to reconstruct with the same ease. In that sense, astronomy is preservation. We are collecting evidence before the evidence thins. This is not dramatic in the ordinary sense. No alarm sounds, no wall descends, no galaxy switches off in a single night. The change is slow, quiet, almost gentle. But, on the scale of the universe, gentle processes can erase entire categories of knowledge. The farthest universe is not only beyond us, it is leaving the archive. That is why the question cannot be answered by imagination alone. It has to be answered by building better instruments, while the universe still speaks in ways we can detect. It requires telescopes in space, observatories on Earth, detectors buried underground, satellites measuring faint radiation, and long surveys that compare millions of galaxies. It requires patience, because the signal is weak. It requires caution, because the wrong pattern can look meaningful when the data is noisy. And it requires humility, because the universe does not provide labels on its largest structures. A faint temperature fluctuation in the cosmic microwave background is not a sentence written for us. A redshift is not a story by itself. A gravitational lens is not an explanation. Each is a clue, and the hidden universe must be approached through clues. This is why cosmology feels different from many other sciences. A geologist can pick up a rock. A biologist can examine a cell. A chemist can repeat a reaction in a lab. Cosmologists cannot rerun the Big Bang, cannot move Earth outside the observable universe, cannot place cameras on the other side of the cosmic horizon, and cannot wait for signals that accelerated expansion forbids. Instead, they use the whole sky as an experiment that has already happened. They look for consistency. They ask whether the same model explains light elements, background radiation, galaxy clustering, lensing, supernova distances, and the growth of structure. They test where the model succeeds and where it strains. They compare the universe at many ages by looking at many distances. They use the past as a laboratory because distance turns into time. And from this careful work, the outline becomes clear. The visible universe is huge, but not complete. The edge is real as an observational limit, but not likely real as a material boundary. The unseen regions probably continue, but their full nature is not directly known. There may be more ordinary space, perhaps vastly more. There may be a finite topology too large to reveal itself. There may be inflationary regions beyond any practical contact. There may be nothing outside the total universe, in the ordinary meaning of outside. And there will certainly be more questions than one species can finish. This is not failure. It is the natural result of being inside the system we are trying to understand. A fish in an ocean can learn currents, pressure, chemistry, temperature, tides, light, and depth. It can understand a great deal about the water around it. But it cannot see the whole ocean at once from outside. We are in a similar position, except the ocean is space-time, and the currents are expansion, gravity, radiation, and dark energy. We do not stand outside the cosmos. We are carried by it. This also means that every answer about beyond must be spoken from within. When we say the universe may be infinite, we say it from one finite patch. When we say it may be flat, we mean our measurements show little or no curvature across the region we can observe. When we say it may continue beyond the horizon, we mean the simplest and best supported models point that way. The language is powerful, but it is always tied to the view from inside. And perhaps that is the most human part of the entire subject. We are not detached witnesses. We are local matter trying to understand a non-local reality. The atoms in our bodies formed inside stars that lived within the observable universe. The light entering our eyes tonight has crossed a limited region of space. The equations in our notebooks were written on one planet, orbiting one star in one galaxy. Yet those equations reach outward and describe horizons billions of light years away. They describe an early universe before planets existed. They predict regions that cannot be photographed. They show where knowledge itself encounters a boundary. That is extraordinary. Not because it makes us masters of the cosmos, because it shows that a small part of the cosmos can become aware of its own limits. The hidden universe may never become visible in full, but the fact that we can understand why it is hidden is already a kind of contact. Not contact with the regions themselves, but contact with the rules that separate us from them. The rules are visible. The full territory is not. There is a final practical image that helps hold all of this together. Picture the observable universe as a spear of ancient messages arriving at Earth. Near the center is the local present. The moon, Mars, the sun, nearby stars. Farther out are older and older chapters. The Milky Way's neighbors, distant galaxies, quasars, early clusters, young galaxies, and finally, the glowing microwave wall of last scattering. Beyond that wall, the universe did not end. Light simply could not yet travel freely. Beyond the outer boundary of what can ever reach us, even later messages are lost to expansion. Now remove the idea that the sphere is the whole. It is only the part addressed to us. Other spheres exist around other locations. Some overlap, some may not. Each one is a private archive of cosmic history, assembled by light and time. No single archive contains everything. The total story, if that phrase makes sense, is larger than any one reading room. That is what lies beyond the universe we can see. More pages, some similar, some possibly different, many unreachable, and perhaps no final cover. This is a quieter answer than fiction often gives, but it is more unsettling. Fiction can place a monster outside the edge. Science places a limitation there. A monster can be faced. A limitation built into space-time cannot be defeated by courage. It can only be understood. And maybe that is why this topic belongs in a calm space documentary. It is not a jump scare. It is a slow realization. The universe is not only bigger than the human world, it is bigger than the human method of completion. We can keep learning, keep measuring, keep correcting, keep reaching, and still the full picture may remain larger than the conversation. The most terrifying edge is not a place where something attacks us. It is a place where the universe simply stops answering. There are also messengers we have only begun to use. For most of history, astronomy meant light. First visible light, then other wavelengths. Radio, infrared, ultraviolet, X-rays, gamma rays, and microwaves. But the universe also sends gravitational waves from colliding black holes and neutron stars. It sends neutrinos from nuclear reactions and violent explosions. It may contain relic backgrounds from processes so early that ordinary light could not carry the message. These messengers matter because each one looks through the universe in a different way. Light can be blocked, scattered, stretched, or absorbed. Neutrinos pass through matter with almost ghostly ease. Gravitational waves move through space as ripples in space-time itself. Future detectors may reveal events hidden behind dust, inside dense regions, or in eras where electromagnetic signals are difficult to read. But even these messengers obey horizons. A gravitational wave from a region whose signal can never reach us is still lost. A neutrino emitted beyond causal contact is still unreachable. A new kind of detector can widen the practical window, but it cannot turn an unreachable region, into a reachable one if space-time itself prevents the connection. That is a key difference between a technological limit and a cosmic limit. Technology says, "Not yet." A horizon may say, "Never from here." This does not make new astronomy pointless. It makes it more valuable. Every new messenger gives another cross-section of the visible universe. It helps us reconstruct events that light alone cannot explain. It can test the early universe in ways that ordinary telescopes cannot. It can reveal hidden black hole mergers, the interiors of supernovae, and perhaps one day signals from inflation itself. But it also reminds us that the hidden universe has layers. Some layers are hidden only because our tools are young. Others are hidden because the universe has arranged distance and time in a way no tool can overcome. A wise civilization would learn to tell the difference. It would not call every unknown impossible. It would not call every possibility proven. It would push instruments as far as evidence allows, while accepting that some questions may end at a boundary no machine can cross. That balance is the real discipline of this subject. The observable universe is not everything. It is the part of everything that has had time to find us. And what lies beyond it may be the greatest reminder that reality is larger than the light that reaches our eyes.